Now I'm really happy to move to actually the last one of our volunteers, and definitely not one of the least. Her name is Shayna Sadai. She will tell us more about her research and also about how she got to become involved in cryosphere research. Shayna, the floor is yours. Thank you.
Good afternoon. Let me just adjust this. And test this. So my name is Shaina Sadai. I am a PhD candidate at the University of Massachusetts, Amherst. And I had a bit of a meandering path into cryosphere research, actually. I began as a researcher in undergraduate work in astrophysics, and I was working on galaxy evolution and formation. And then I transferred into a master's program after I graduated, and that was in applied mathematics. And there I began working on quantum mechanics and Bose-Einstein condensates and a little bit of gravitational waves. And then from there, I found my way into climate science almost on accident. I had taken a class on climatology, and it was extremely interesting. And with the background in natural sciences and mathematics and some modeling work, it was a fairly smooth transition to beginning a PhD and starting to work on climate modeling and ice sheet modeling. And so the talk that I will be giving today is looking at a little bit of the work that I've been doing throughout my PhD. Almost ready to wrap that up. Okay, so let's begin with why we're all here. So we are at the UNFCCC Conference of the Parties 26th session, and the UNFCCC was brought into being back in 1992, and this was the first really large-scale international collaborative effort to do something about climate change. And then science had been growing and advancing up until that point, and it was really starting to become clear that something needed to happen. And so the UNFCCC has the objective within Article 2 of preventing dangerous anthropogenic interference with the climate system. However, dangerous anthropogenic interference was not fully defined within that agreement. And so the resulting Conference of the Parties meetings that have happened since then have been to try to define how we're going to do this. How are we going to prevent dangerous anthropogenic interference? And how are we going to accomplish all of the other aspects of responding to climate change? Adaptation, we have mitigation, we have finance, we have aid and technology transfers. And so we've been working on that over time throughout these COP meetings. And of course, as we all know, at COP21 in Paris, France, we had the Paris Agreement, which had the objective of stabilizing global mean surface temperature at 1.5 degrees Celsius or 2 degrees Celsius below the pre-industrial average. And so that is where we are with our global goal for climate action. And so one long-term impact of climate change is, of course, sea level rise. And sea levels have been rising pretty steadily and at an accelerating rate in more recent decades. And we know that this is pretty far outside of what the normal natural climate variability would be. We are seeing big changes as a result of thermal expansion of the oceans, as a result of changes in the ice sheets where they're beginning to destabilize as a result of changing mountain glaciers, and several other more minor impacts also feed into sea level rise, which has a distinct regional variability. And so projections currently are showing that this is going to be a very long-term issue that we're going to be dealing with into the future. Sea levels will continue to rise for several centuries going forward, and then they will stay elevated for several millennia. So we need to start to think about how we can mitigate to try to prevent a lot of this from happening, to try to make sure that the ultimate magnitude of sea level rise is as low as we can keep it. And then, of course, how we can adapt to that. And so for each of these different contributors to sea level rise, we try to model what the contributions are going to be. And I particularly work on the Antarctic ice sheet. And so as you can see in these plots, these are from the the most recent IPCC report, AR6, Working Group 1. And so you can see that this is going to be a distinctly long-term implication. And it also has an uneven distribution in terms of space. So the oceans are not like a bathtub. The water is not rising evenly. It's rising in different ways in different places. And so Antarctica in particular is quite central to our climate system. It's very remote, it's far away, so it's not on our minds all the time. And so there's going to be two main impacts that I'm going to talk to you about with regards to Antarctic destabilization. And the first is, of course, the sea level rise, which will be long-term, it will be irreversible, and it will have an uneven spatial impact. And the second is feedbacks on the global climate system, because as Antarctica starts to melt, that meltwater has other effects. Instead of just contributing to sea level rise, it's also changing things about ocean circulation. It's also changing sea ice distributions. So there are implications of that for the Paris Agreement and specifically the temperature goal. These are movies that are not playing. That's fine though. So this is the first chapter of my PhD dissertation work was trying to look at what this impact of Antarctic melt is going to have on global climate. And so climate models, they are state of the art. They are incredible pieces of technology, but there's always room for improvement. And one of the areas for improvement is specifically with the introduction of dynamic ice sheets into global climate models. Currently, there are not fully operational dynamic ice sheet models within climate models. And so what we do to try to assess the impact of meltwater on global climate is to take predictions from an ice sheet model and feed those into a global climate model. And so that's what I did. I took some results from an ice sheet model that predicted how much melt was going to be coming off at different times, and then where it was going to be coming off of. So which glaciers in Antarctica were starting to go at which points in time. And the results of those simulations, when I ran those climate models, were that there were these competing feedbacks that were happening as that meltwater starts to enter the ocean around the continent. It sort of stratifies the water column. It makes the water column so that it's not moving in the same way it used to before. It's not having a vertical circulation. And that means that heat, which would normally come up to the surface and be distributed up through the air, is getting trapped at depth. So warming below the surface levels of the ocean. While at the same time, the meltwater makes it, because it's freshwater, it makes it a little bit easier for ice to form on the surface of the ocean around the continent. And that means that we have this growth of sea ice, which is a little counterintuitive because, of course, this is still a warming scenario. These are high emission scenarios that I was running. And so we have this warmth at depth and this cooling at the surface. And that has implications for, of course, ice sheet stability itself. Also supposed to be a movie. I apologize that these are not running. But what they would show is that on this side, these are screenshots of the first thing. So under a high emission scenario, we have the impact that meltwater would have, the difference that would make if you include the meltwater from Antarctica versus if you don't include it. You can see that the global climate model, the average surface air temperature is going to be a little bit cooler when you consider the loss of Antarctic ice sheet regions around the periphery. But we have to remind ourselves that we are still in a high emission scenario where I'm running these simulations. And so it does get quite warm. The average surface air temperature is still rising. It rises at a slower rate as a result of the ice sheet collapse. So still warming, but not warming quite as quickly. So that might sound on the surface like good news. Oh, the temperature is not rising as fast. But that would be a dangerous line of thought, because it's never good to have an ice sheet start to destabilize because we have that impact of sea level rise. So something that might sound on the surface good in terms of the Paris Agreement goal in terms of global mean surface temperature, well, if the temperature is rising slower, then maybe we have more time before we surpass that goal. But we cannot think of it that way, because that would be at the expense of island nations and coastal communities who are the most impacted by sea level rise. And so when we look at sea level rise under the Paris Agreement, this is work that was published by DeCanto et al. In Nature in just this past year. And so these are the same ice sheet model that I was using for predictions to run that global climate model. And these ice sheet model simulations looked at what the contribution to sea level rise from the Antarctic ice sheet would be under the Paris Agreement goals versus if we go past those goals. And so over here, we can see that at 1.5 degrees Celsius, we still have a very long-term contribution. So looking out to 2300, there is still a full meter of sea level rise solely from Antarctica, not even considering Greenland or thermal expansion or any of those other components. So this is low end the estimate. The real amount of sea level rise would be much higher. But just from Antarctica, even under 1.5 degrees Celsius, we have multiple centuries of sea level rise contribution. If we look at the other side of the plot, the 3 degrees side, currently the nationally determined contributions that countries have submitted under the Paris Agreement only get us to about 2.7 degrees of warming by the end of the century. So not good enough to meet the Paris Agreement goals at all, and a very dangerous amount of warming, and particularly a very dangerous amount of warming in terms of ice sheet stability. And so as you can see there, still a multi-centennial rise, of course, but much higher. So the lower that we can keep the temperature rise, the safer we will have the ice sheet and the less of an impact we will have from sea level rise. And what about carbon dioxide removal? This is also results from that same paper, DeCanto et al., 2021. If you have carbon dioxide removal, we all know under the Paris Agreement, we're trying to think about ways right now that we can lower the surface air temperature. So maybe sucking CO2 out of the atmosphere, bring the surface air temperatures down, that can help us meet the Paris Agreement goals. However, sucking CO2 out of the atmosphere is, first of all, untested. So it's not currently achievable at scale. It's very dangerous to rely on that sort of thing. But it's also particularly dangerous for the ice sheets, because while you can have an overshoot pathway where you overshoot the Paris Agreement goals and then bring the temperature back down, overshoot may work for surface air temperature, but it does not work for sea level rise. Once that sea level rise is committed, you are not bringing it back down. It will stay elevated for millennia. So we have to think about this when we're thinking about solutions and how we're going to achieve the temperature goal. We have to think about not relying on things like overshoot pathways and negative emissions to try to make us safer, because it will not work quite that way. As you can see, this is showing, depending on when carbon dioxide removal is initiated, the later it's initiated, the higher the sea level rise impact is, but really, we should not rely on this. And this is just showing the importance of looking long-term out to 2500, even if we remove a lot of carbon dioxide. This is a really quite substantial contribution to sea level rise solely from Antarctica. And so the meltwater feedback, as I said before, it also impacts ice sheet evolution. So when my simulations are showing that the surface air temperature rise is delayed, that surface air temperature rise being delayed delays melting on the surface of the ice sheet. And so it delays the overall collapse of Antarctica. And so this is looking at when you consider, if we look at solely the red line and the blue line over these, the red line are simulations when you don't consider melting of the Antarctic ice sheet and the impacts it has on global climate. And the blue line is when you do consider those. And so you can see when you do consider the meltwater feedback and the delayed surface air temperature rise that comes with, you have a delay in when Antarctica collapses. But still a very high rate of sea level rise. So looking at these two things together, the feedback that Antarctic melt has on global surface air temperature rise, that's what's shown here in red. And the blue line is what I just showed you, that delay, the sea level rise contribution that delay still is coming with. So you can see, looking here, that sea level rise is still a substantial number of meters going into the future, even at the same time, looking at the red line, as we have a delay in surface air temperature that could be 1 to 2 degrees. So these are an important climate justice consideration to think about. And so new work that's just going into peer review right now is looking at the climate justice implications of these two things, the sea level rise and the negative feedback on surface air temperature rise. And we have assessed procedural, recognition, and distributive forms of justice considerations. Procedural meaning how power dynamics play out within a negotiating process, distributive meaning how impacts vary in terms of space and time, and recognition being recognizing the existence rights of cultural and social groups. And so this research will be forthcoming. I just want to highlight one particular part of it for now, which is the spatial distribution of that Antarctic component of sea level rise. So I talked a lot about how it's long-term, it's multi-centennial, and sea levels will stay elevated. This is showing the spatial variability just of that Antarctic contribution to sea level rise. And so the thin pink line that you can see, that is where global mean sea level values are existing. Everything north of that is where locations that will have a higher sea level rise contribution from Antarctica than the global mean. And I've plotted here the locations of the Alliance of Small Island States, because they have highlighted continuously in their strong history of advocacy within the UNFCCC that sea level rise is a pressing concern in particular for island states. And so the paper discusses what are the impacts of Antarctic contribution of sea level rise on these places. And that with calculations, I've seen that it's 11 to 33% higher than the global mean is the amount of sea level that will be expected in each of these places. And of course, every one of those nations is very different types of geomorphology, different types of islands, different they're all, every place is unique. Every place in the world is unique. And so how those values actually play out on the ground and impact people living there will vary, of course, as well. But what we wanted to highlight was that this is an uneven contribution, that they will be receiving a higher level of impact compared to the global mean. And so some key takeaways here are just that we have to consider the long term. We have to be thinking not just to 2100. We have to be thinking farther than that, because this is an issue of intergenerational and multi-generational recognition justice. And we need to be thinking about what future generations are going to be dealing with as a result of near-term policy, because near-term policy is what's going to dictate whether or not we pass threshold points of Antarctic stability. And those threshold points are thought to lie somewhere between 1.5 and 3 degrees Celsius, but 3 degrees is an extremely dangerous point. So we want to keep it to as close to 1.5 C as we possibly can. And so we need to consider all of these factors. We need to consider, of course, global mean surface temperature, but how that interaction interplays with sea level rise and how that impacts people. Because we're not thinking just in terms of these physical changes to the Earth system. We care about this because we care about the impacts. So thank you very much for your time. I'll take any questions if you have them. So the question was about the 3 different types of justice. Oh, I can't go back. I will just say them. So the 3 different types of justice that were considered were procedural, distributive, and recognition justice. And so for procedural justice, what we were looking at was what were the power dynamics at play within the negotiating processes of the UNFCCC from 1992 to the Paris Agreement, and of course from then on, but the paper is really assessing up until that Paris Agreement point. And so we were looking at, well, what were AOSIS states advocating for, especially in the early time periods? And they were advocating for binding emissions reductions, get those emissions down, get them down at a set rate. But we ended up, of course, with a temperature target, which is much different than a binding emissions reduction target. So we were looking at what was leading to that transition point. How did that play out? And it's a very complicated story, so I won't go too into it, but basically it's a lot of political ramifications, especially some political developments within the United States that made the US negotiating position specifically more in favor of not the binding emissions reductions, which of course we saw in the Kyoto Protocol, because the Kyoto Protocol was the first attempt at a binding emissions reduction under the UNFCCC. So that was the procedural justice, just trying to look at how we went from we want to prevent dangerous anthropogenic interference to, well, what if we have binding emissions reductions to now we have a temperature target based on global mean surface temperature. So how did that occur? Recognition justice is looking at the existence rights of cultural and social groups. And so we were really trying to look at whose voices are strongly represented. And of course, there's lots of UN negotiating bodies, but there's also just individual people. Like how are the needs of indigenous and local populations being heard throughout these processes? Whose land is going to be most implicated? And also how do historical factors play into that? So what was the impact of colonialism on sea level rise vulnerability in different locations? And so that's all a very key consideration into recognition justice. And then the other one was distributive justice. And so for that, I was looking mostly in terms of space and time. So spatial and temporal variability of sea level rise, thinking long-term, thinking about overshoot pathways, thinking about how we use 2100, and then of course the differences in sea level rise distribution from an Antarctic ice sheet. Sorry, that was a lot. The paper is very long, as you might guess.
Fantastic. Thanks so much, Shayna. That was really interesting, like the relationship between the mitigation and adaptation aspects there.